Hey everyone, welcome back. Today, we're diving deep, really deep, into the fabric of reality itself. For almost 100 years, we've had this pretty reliable map of the atomic world, but it's always been a little bit blurry. Well, some new research is proposing a brand new set of conceptual lenses, ones that could bring that map into incredibly sharp focus. So let's take a look at what this new lens can actually show us.
That's the fundamental challenge of quantum mechanics, right? You can't just look at an electron and see what it's up to. Instead, we have to build models, these mathematical pictures, just to describe its behavior. And for a very long time, our best picture has come from one of the absolute giants of physics.
So, before we peer through this new lens, we really need to get a handle on the map we've been using all this time. Let's start with that classic picture of the atom that has served science so incredibly well for nearly a century.
Erwin Schrödinger's equations, they gave us this idea of electron orbitals. And they're not like tiny planets zipping around a sun. Nope, they're more like clouds of probability. These fuzzy regions where an electron is most likely to be. This model has been unbelievably successful. It's pretty much the bedrock of all modern chemistry and physics. It's our go-to guide for the subatomic world.
But, this brings up a really important question. The Schrödinger model is super powerful, for sure. But what if there are deeper layers of order and interaction that it just doesn't quite capture? What about those tricky problems, like predicting the exact energy of a complex atom, or the way a chemical reaction actually unfolds? What if we've been missing some crucial details, hidden in all that quantum noise?
And that right there is where this new research comes into play. It doesn't throw out that old map, not at all. Instead, it offers a new set of tools, a new lens, you could say, that's designed to bring the quantum world into focus with just stunning clarity.
Okay, now don't worry, we're not going to get lost in a bunch of complex math today, I promise. Instead, we're just going to focus on what these three conceptual tools are designed to do. Think of them like three different settings on a new kind of quantum microscope, where each one is built to reveal something totally unique.
All right, tool number one is all about entropy, and entropy is really just a fancy scientific way of measuring disorder. Think about the difference between a perfectly stacked deck of cards and that same deck after you've shuffled it like crazy. This formula is designed to measure that exact quantum messiness, which helps us pinpoint the most stable, most organized states, basically finding those little moments of calm in the middle of a quantum storm.
Now this is where it gets really interesting, because this is all about relationships. This second tool, it helps us find the optimal point of coherence and coupling. In simpler terms, that's the absolute sweet spot where all the particles are working together perfectly in sync, kind of like a perfectly tuned orchestra, interacting in the most effective way with each other and with the nucleus.
And this is the final piece of the puzzle, the third tool. They call it the Superformula Synchrony, and it basically acts like the master conductor of that orchestra. It's designed to model all the super complex interactions that are happening all at once. I'm talking about things like vibrations and resonances that affect the entire atomic structure. It's trying to capture the whole symphony of the system, not just the individual notes.
Okay, so we have these three really powerful new tools, but what happens when we actually combine them? What kind of new details start to pop out when we apply this complete lens to our existing quantum map?
So here's how it all comes together. It's kind of like a simple four-step process. First, we use that entropy formula to measure the disorder and find those really stable states. Second, we pinpoint that optimal moment of interaction, that perfect synchrony. Third, we use the superformula to model the entire system symphony. And the result of all of this? We can finally make predictions that are way, way more accurate. And these are not just some abstract predictions either. We are talking about fundamental properties that literally drive the world around us. We could predict with much greater accuracy how much energy it takes to rip an electron off an atom. That's your ionization energy. We could better understand electron stability. And maybe most importantly, how and why chemical reactions actually happen.
So you see, this isn't about applying just one little trick. The real power here comes from combining all of these tools into one unified, multi-dimensional approach. It's about looking at stability and interaction and the system's dynamics all at the exact same time to get the complete picture.
And hey, that's not just my opinion. The author of the paper, Luis Fernandez Carbonell, he puts it perfectly. He says, this isn't just some academic exercise. It's about opening brand new doors for research and, just as important, for real-world technology.
So, let's actually walk through some of those new avenues. Let's explore what this could really mean for the future.
What happens when our fundamental understanding of reality gets a major upgrade like this?
Well, when you can more accurately predict how atoms are going to behave, you can start designing things from the ground up, atom by atom. I mean, think about creating brand new materials with specific properties we've only dreamed of, or designing more efficient catalysts for chemical reactions, or maybe even developing entirely new forms of quantum computing. A clearer map means we can finally navigate to some incredible new destinations.
So, I'll leave you with this thought. For decades, we have built our entire modern world on a slightly fuzzy picture of reality. Now, if we can finally bring that picture into sharp, crystal-clear focus, what new possibilities are we going to see? What becomes buildable tomorrow that seems like pure science fiction today?